Okay, welcome again. See, what we have discussed in this course till now is how a microprocessor works basically. So we have seen that you have a microprocessor which is used to basically execute the program which is stored in some memory. So you have a memory which is basically a storage device which stores the instructions as well as this data. And then there are several buses. You have address bus, data bus, and then you have control bus. Okay, so this is your 8085 processor. So the instructions they are stored in this memory, and how we store the instructions in this memory that we have discussed in the last class. Okay, so once you store the program in the memory, and once the processor starts executing the program, so it first identifies the memory location from which it is going to execute or fetch the next byte. So that address is placed on the address bus, so that location is identified. Okay, and then it sends a control signal that is read. So the data on that location is placed on the data bus and it goes inside the processor. Inside the processor it is given to the instruction decoder, so which decodes this instruction, means which comes to know that what is the task of that instruction basically. Okay, and then that is executed accordingly in the arithmetic and logic unit or any other circuit. Okay, and all this operation is basically controlled by the timing and the control circuit. Okay, so we will discuss that in more detail when you come to the detailed architecture. So, but right now I am not going into the detailed architecture. Before going into the detailed architecture and the pin diagram of this processor, so we still need to have some background or some foundation for this course. Okay, so in 8085 programming model that we will discuss today, so it is a basically model which gives you an idea that what are the registers available in 8085 to the programmer. Okay, so there are certain registers which are used only by the processor and they are not accessible to the programmer for programming. Okay, but there are certain registers which we can use for programming, and we will discuss some of those. So if you see in your 8085, you have 6 general purpose registers. Along with that, one register is called as accumulator. A. Then we have flags. This is a new concept that we will introduce today. Then we have register B, C, D, E, H, and L. Okay, and all of these are 8-bit registers. Okay. Apart from this, you have two 16-point registers which act as memory pointers. One is called as program counter (PC) and one is stack pointer. Both these registers, they are 16-bit registers. Okay, so PC, it stands for your program counter, and SP stands for your stack pointer. Okay, and the information between the processor and the memory, okay, so that is communicated using data and address bus. So you have address bus which is 16-bit, so we have 16 lines here and it is unidirectional. Okay, so the data can go from processor to the memory only. Okay, whereas your data bus It is bidirectional and it is 8-bit. Okay. So now if you see what is the function of these resistors, let us first turn to resistors. So you have 6 general purpose resistors, 8-bit resistors B, C, D, E, H and L. Okay. So we call them as general purpose resistors. Okay. So they are used by the programmers to store 8-bit data during the execution of the programs. Okay. So they are accessible to the programmers. Okay. And moreover, so you can use these resistors, general purpose resistors, as individual 8-bit resistors. Otherwise, you can combine them in pairs as well to form a 16-bit resistors. Okay. So it means you can combine B and C to get a BC pair. This is called as a resistor pair. Similarly, D and E, they can be combined to store 16-bit data, and H and L, they can also be used to store a 16-bit information. Okay, but the pairing is unique. Okay, it means if you want to pair two resistors, so B and C is the only combination. You cannot pair B with E. Okay, or you cannot pair D with C. So whenever you have to use a resistor pair, you have to use a BC pair or a DE pair or a HL pair. So they can be used to store 16-bit data, or they can be used in the you will see in the data copy instructions to copy 16-bit data as well. Okay, so these are called as general purpose registers. Okay, so anytime if you want to store 8-bit data, suppose you want to add two numbers, so you may store one number in B and one number in A, so you can add them. You can find some logical operation or whatever you want to do. Okay, depending upon the instructions available, so you can perform any operations. So these 6-bit registers are available inside the microprocessor, which are accessible to the programmer for programming. Okay, now apart from these 6 general purpose registers, you have a very important registers in the microprocessor, which is called as accumulator, and this is of course also 8-bit register. Okay, and this accumulator is basically part of your ALU. Okay, register A, which we call as accumulator. This is the most widely used register in the microprocessor. Okay, because all the arithmetic and logic operations in the ALU, okay, so ALU is supposed to perform these arithmetic and logic operations. Okay, so all the arithmetic and the logic operations, in all the arithmetic and the logic operations, accumulator is used as one of the operands. Okay, it means if you have some, this is ALU, when you will see the architecture also, so you have to perform some arithmetic or logic operations between two 8-bit numbers. Okay, so you give one number here, one 8-bit number here, the ALU will perform the operation and give you some output. Okay, so out of these two operands, which are called as operands, one operand is always stored in A. Okay, one of the operands is always stored in A. The second operand, it can be in register B or C or D, E, H, L, or it can also be a 8-bit number which is located in some memory location, or you can directly supply a 8-bit number when you discuss this instruction move immediate, it will come. So you can find the arithmetic or the logic operation between the 8-bit number which is stored in A with another number which is stored either in these general purpose registers, or it may be stored in some memory location, or it may be a immediate direct 8-bit number, suppose 32H. Okay, so one of the operands has to be A. Okay, so one input is fixed to the ALU. Okay, the another input that can come from register B, it can come from C or D or E or H or R, or it can come from some memory location as well, or you can directly supply 8-bit number for performing some arithmetic operation. Okay, this is what is the significance of this register A. Okay, and whenever you perform any arithmetic operations, the operation is now performed between A and some other 8-bit number which is stored in registers or memory, or it is immediate 8-bit data, and the result is going to be stored finally in accumulator A as well. Okay, so it means if you write instruction suppose add B, so when you write add B, we have just specified one operand, that is B. It means one number is in register B. So where is the second number? We have not specified it because it is implicit. Okay, if you are using arithmetic operation, you have to just specify one operand, that is B. The second operand has to be in A, so you need not to specify add A comma B. You do not write like this, the instruction add A comma B. It means you have to add two numbers in A and B, A plus B, and that gets stored again in A. This is not the mnemonic. Okay, because whenever it is a arithmetic operation, one operand, the first operand is always in accumulator A. So that is why in these instructions this second operand A is implicit. Okay, so what this instruction will do, it will add the contents of register A with register B, and the data is stored finally in register A. Okay, so the sum of A and B, it goes to A. So if you write instruction add B, if you have a sequence of instructions add B, then you write suppose add C, then you write add D, what will happen? This instruction will sum basically the contents of A and B, and the output is stored in A. Now when you write add C, the contents of A plus C are added and it goes again into A. Okay, it means whatever is the output of the first instruction A, now it is again added to the contents of C. Similarly, when you write add D, so A plus D is added and it goes to A. Okay, so the previous sum, it now comes here, it again gets summed up with the contents of register D and it goes to A. This is what is the this what gives this name accumulator. Okay, so it accumulates the data. Okay, you go on using some arithmetic operations like addition, so the data gets accumulated in the register A. This is what is the name. This is why we call it as accumulator. Okay, it is used to accumulate the data. So it is not like that. Okay, it is accumulator A, so we have written it as A. A stands for accumulator. This is not the concept. Okay, the concept of accumulator is that it is used to accumulate the data. Okay, and it is not necessary that in every microcontroller or processor you will denote accumulator with A. Okay, so there are different notations. So in some notation you may suppose have a notation or not for accumulator. Okay, you can have some notation X, Y, Z, anything you can have for accumulator. Okay, so A does not stand for accumulator. Accumulator means that when you perform some arithmetic operation like addition, so the data which is summed up, it gets stored or accumulated in this register A. Okay, so A is a very important register in your microprocessor. All the arithmetic and the logic operations, in all those operations, first operand will always be stored in A. Okay, so you cannot directly add the contents of B with C. You cannot directly contents of D with some memory location. Okay, or you cannot directly add a number with some contents with B. You cannot add B with C directly. You cannot add the contents of some memory with some register, general purpose register B. This is not feasible. You cannot directly add a 8-bit number with the contents of B, C, D, any register. Okay, so all these operations, they are invalid in 8085. Okay, so if you have two numbers which are stored in B and C, and if you want to add them, so what you have to do? You have to move one data into A, either B or C. You can transfer this data into A, and then of course you can add the contents of A with C, and the result will be stored in A. Okay, so I hope I am clear about this register A, so which is very important register, 8-bit register in 8085, which is called as accumulator. So we have in the programming model, so we have so far we have general purpose registers, so which are B, C, D, E, H, and L. So they can be used either 8-bit registers, or if you want you can combine them in register pairs B, C, D, E, H, L. Okay, so they are used by the programmers when you write the assembly language program. They are used. Okay, see, an assembly language program, this is a very important thing. In when you write some programs in other languages, maybe in high level languages, so you have some integers. Okay, you define some variables. Basically you define A, B, C, whatever you want. Okay, so you can define 3 variables, 10 variables, 100 variables. It is up to you, right? And you can store the data in those variables. But this is not the case with assembly language. Okay, so the variables here are basically in the form of hardware. Okay, so you have registers here to store the information. You store the information in registers, not in the variables. Okay, and these registers are fixed. Okay, so whatever information you have to store for any arithmetic and the logic operation, that must be stored in one of these registers. Okay, and when it comes to arithmetic and the logic operation, one operand has to be in the accumulator. The second operand can be in the register, it can be in the memory, or it can be any 8-bit number. Okay, and then there comes one more important register that is called as flag register, which we have mentioned in the programming model. Flag register, or we call simply it as flags. Okay, in fact it is not a register. Okay, see, flags are basically flip-flops. Okay, so there are 5 flip-flops or 5 flags in 8085. We call them as carry flag, Sine flag, zero flag, parity flag, and auxiliary carry. Okay, carry, sine, zero, parity, and AC, auxiliary carry flag. What are basically flags? They give the status of an operation. Okay, see, like just I have said that whenever you perform some arithmetic operation or logical operations in the ALU, so one operand must be in A. The second operand can come from any register B, C, D, H, L, or memory, or it can be a 8-bit number. Okay, when you perform the arithmetic and the logic operation, okay, the result is stored of course in A. Okay, so it is A plus some data which can come from this B, C, D, H, L, or from memory or 8-bit number, and the result is stored again in A. Okay, So what these flags basically represent, they represent the status of the result which is stored after a arithmetic or a logical operation. Okay, the result is stored in A, but what is the status of that result? That basically comes in these flags, which are basically flip-flops. So they are set or reset according to the contents of accumulator. So whenever you perform any operation, logical operation or arithmetic operation, the result is stored in accumulator A, and depending upon that result, okay, depending upon the result which is stored in A, so these flip-flops, they are set or reset to show certain status signals. Okay, so like suppose if you say zero flag, zero flag, so it is set if the result in the accumulator is 0. Okay, and it is set if the result in the accumulator is not 0. Okay, it means Z will be equal to 1 if the contents of A are 0, and Z is equal to 0 if A is not equal to 0. Okay, this is what is the status of this flag depending upon the results that you get in the accumulator. Okay, so if the number that is stored in the accumulator after some arithmetic or logic operation, it is 0, your 0 flag will be set. If it is not 0, it is reset. Okay, and these flags, they are also accessible to the programmer, and they play a very important role when you discuss these conditional instructions or the jump instructions. Okay, so they are used to control the to transfer a program to a different location. Okay, using the status of these flags. Okay, like this instruction, jump if 0, jump if not 0. Okay, so this instruction will basically check the status of the 0 flag. Okay, if it is 0, it will jump to a particular location that you have to specify in the address. Okay, if it is similarly jump if not 0, this will jump to the particular memory location for which you have to specify the address if the result in the accumulator is not 0. Okay, and most of these flags, they are affected by arithmetic and logic operations, and they are used to, you can say, assess the contents or the status of the data in the accumulator. Okay, but certain flags, you see, they are also affected by the operations or the data in some other registers, like if when you say decrement and the increment. So if you increment and decrement the data on any register, maybe in register B or C, okay, so the flag can also be used to check, the 0 flag can be used to check the status whether the data is 0 or not. Okay, and this we will discuss when we will discuss the timers and the counters. It is a very important use of the 0 flag, of course. Let's suppose you want to make a loop or a counter which should run 100 times or whatever number of times you want to run it. So how you do that? So you load some number into a register. Okay, let us suppose I load register B with a count 10. Okay, in decimal, of course. Okay, and then I started decrementing. Okay, decrement B. So how I am getting, how we will get to know that whether this loop has executed 10 times or not. Okay, how you can check it or how you can verify it? So for that we can use 0 flag. Okay, every time you decrement it, the register will go from 10 to 9 contents. The next time when you decrement it, it goes from 9 to 8 and so on. Okay, and then you have to see whether it is 0 or not. Okay, if it's not 0, jump if not 0, you have to go back, you have to repeat again this loop. Okay, jump if no not 0 again. So of course we have some program here which is used to serve some purpose. Maybe it is used to just create a delay like we use in the traffic lights. Okay, so you have a program which is used to create some delay and to create that delay you may need to run a loop many number of times. Okay, so you have to come out of this loop when the counter resets to 0. So that can be checked using this flag. Okay, so as long as this data is 0, you will again jump to the main program, again execute it, again decrement the resistor b, check it whether it is 0 or not. If it is not 0, go back and so on. Okay, so once the data in resistor b becomes 0, so this program will now not be transferred to this location, it will come out of this loop. Okay, so similarly you have so many other flags. So 0 flag is used to check the status of the data in a accumulator or in some other registers. Depending upon some instructions, it is not for all the instructions. Okay, so that we will come when we will study these instruction detail, how the flags are affected by the various instructions, of course. Okay, so don't worry about that. So if the so right now just look to this register A. So if the contents of A after some arithmetic and logic operations, if it is at 0, a 0 flag is set. Okay, if they're not 0, it is reset. Similarly, if you say the sine flag, they are basically used to indicate whether the result is positive or negative. Okay, and if you go to the signed number representation, so how we classify the signed numbers into positive and the negative numbers. So we just look at the most significant bit. So if I have a data 0 1 1 0 1 1 1 1, okay, so whether it is a positive number or negative number. So in the signed integers, the most significant bit MSB, it is used for sign representation. So if it is 0, it is positive. So if I take a number 1 0 1 1 0 0 1 1, so the most significant bit here is 1, so it is a negative number, it is a positive number. If you see for the signed numbers, okay, if you go for the unsigned numbers, of course then positive and negative does not have any meaning. So then all the bits, they just represent the magnitude. Okay, but if you have signed integer format, in that case the most significant bit of this 8-bit data will represent whether it is a positive or a negative number. Okay, so if it is 0, it is positive. If this most significant bit is 1, it is negative. So accordingly you can see what is the role of sine flag now. Okay, so sine flag will indicate whether the result in the accumulator is positive or negative. Okay, and how you check it. So you have to just see the sine flag. If it is set, it means it is a negative number. If it is reset, that is if it is 0, so it is a positive number. Okay, so sine flag is set if the most significant bit is 1. Okay, and if the most significant bit of the data is 0, it is reset. Okay, it means even then whenever the number is negative, basically it will be set. Okay, and see again this sine flag is also used for jumping and this control operations. But one more important application of this flag that I would like to discuss is, see, when you compare two numbers, so we have discussed this 0 flag. Okay, so it is set whether its contents or 0. If it is not 0, it is reset. Okay, then another flag that we are discussing is sine flag. So sine flag here, sine flag is when if MSB is 1. Okay, and it is reset or its status is 0 if this is 0. Okay, it means if the number is negative, it is set. If the number is positive, it is reset. So see what is the application of this sine flag. I will give one example. Suppose you want to compare two numbers, okay, using a microprocessor, that which one is smaller or which one is larger, okay. So how you can check it? Yes, so you have to simply find the subtract, okay. So one number has to be in accumulator A. The second operand, it can come from anywhere. It can come from the general purpose registers, it can come from some memory location, or it can be a direct 8-bit number, okay. And when you perform this subtraction, the subtraction has to be done between A and some other 8-bit data, okay. You cannot subtract the contents of A from B or A from C. The first operand is A, okay. So it is always A minus something, right? A minus B, it can be A minus C, A minus some data in the memory, or it can be A minus some 8-bit number directly, okay. And after this, the result is, of course, it is again stored in A, okay. Now my question is that if you want to use Sine Flag to compare two numbers, what you can do? So you have to simply put one number in A, and the second number you can put in any of these registers B, C, D, H, L, okay. And then you perform the subtract operation. You write the subtract instruction, okay. So when you write the subtract instruction, what will happen? If the contents of A are greater than the contents of B, it means your number is positive, so your Sine Flag will be 0, okay. If the contents of A are less than the contents of, if the number in A is less than the number B, or B is greater than A, in that case the result will be negative and your Sine Flag will be set, okay. So by checking whether the Sine Flag is 0 or it is 1, you can compare that which of the two numbers is greater or lesser, okay. And when you will see, when you write the programs, suppose you have a set of data stored in a memory location and you have to write a program to add only the positive values, okay, you have to ignore all the negative numbers. So in that case you take the help of the Sine Flag, okay. So every time you subtract the two numbers, you have to check the status of Sine Flag, whether it is positive or negative. Or simply, if you have, suppose, so this is how you use the Sine Flag, okay. And similarly, you have three more flags. One is carry flag. Now I think this must come to your mind, what is the meaning of this, okay. So whenever a carry is generated from the most significant bit, okay, your carry flag will be set. Suppose I add two numbers 1 0 1 1 0 0 0 0 and 1 0 0 0 0 1 1 1, okay. So this is in A, this may be supposed in B, and you write add A, add B. So the contents of these will be added and the result will be stored finally in A. So it is 1 1 1 0 1 1 0 1 plus 1 0 carry 1, okay. So since carry is generated using this operation, so the carry flag will be set 1, okay. So carry will be set 1 if carry is generated from MSB or we say bit D7, okay. D7 means it is like this: D7, D6, D5, D4, D2, D1, D0. So these are different bits of 8-bit number: 0 1 2 3 4 5 6 8 bits, okay. So whenever any arithmetic operation, it results in a carry from D7, bit D7, your carry flag is set, okay. So if there is no carry, of course it is reset, okay. Again, you have instruction jump if carry, jump if no carry, and so on, okay. So they are come under the classification of branching instructions, okay, where you transfer the control of program to a different location depending upon the status of flags. So flags are nothing, okay. So flags are simply flip-flops. There are 5 flip-flops, so they are set or reset according to the status of some arithmetic and logic operation. And most of these flags, they check the contents of accumulator except some instructions. Okay, so what is the result of some arithmetic and logic operation? That result is stored in A, and what is the status of that result? That comes to flags. Okay, so one thing is very important to note here. When you write some program, suppose you write a program, you have some data in A and B, and you write a program, move, let us suppose A comma B, and then you write add C. Okay, then you can write add B or subtract D and so on. Okay, now say right now when the processor will execute this instruction, this is a data copy instructions, move the contents of B into A. Okay, so that data copy instructions, they do not affect flags. Okay, this first thing you must note. The data copy operations, they do not affect the flags. Okay, it is because of the arithmetic and logic operations only which affect the flags. Now when you write add C, okay, so this instruction will add the contents of A with C and the result will get stored in A. Okay, now once this instruction is executed, so the flags, the 5 flags, your carry flag, 0, sign, parity, and auxiliary carry. Okay, this status will be updated accordingly. Okay, according to the result in this register A. So if a carry is generated, okay, carry flag is set. If the result in the accumulator is 0, your 0 flag is set. Okay, if the most significant bit is 1, means it is a negative number, your sign flag is set. Okay, similarly there are 2 flags, one is parity and one is called as auxiliary carry. Okay, so parity flag is set if the result has even number of ones. Okay, it is set to 1 in case of even number of ones. Okay, so if in the accumulator, like suppose if this is the result in the accumulator, so whether parity is set or reset, so you have to count how many ones are there, 1 2 3, so it is odd, so it means your parity will be 0 in this case. Okay, if you see to this number, if this is the result of some operation in the accumulator, so we have 1 2 3 4. Okay, so 4 ones are there, so this number is even, so it is used to check even and odd parity. Okay, so in this case your parity flag will be set to 1. This is what is the parity flag. Okay, and auxiliary carry, basically it is set when during some arithmetic operation there is a carry from D3 to D4. Okay, and it is used for generally for the BCD addition. Okay, that you know how we add the BCD numbers. Okay, one recorded decimal. So whenever some arithmetic operation, it generates a carry from D3 to D4 bit, this auxiliary carry flag is set, otherwise it is reset. Okay, so coming back to this, so you have written an instruction add C. Okay, so the contents of A, they are get added with the contents of C and the result is stored in A. Now according to the contents of A, the status of these flags will be updated, isn't it? And then you write again another instruction add B. The contents of A will be added with B and the result again gets stored in A. Now the status of flags after this instruction will be different. Okay, so the status changes from instruction to instruction. Okay, of course in between if you have some instruction which does not affect the flags, if in between this I write one more instruction, move C comma D, so this instruction will not affect the flags. So what is the status of flags after this instruction? It will return. But if you immediately write instruction add B after add C, the contents of accumulator will be now changed, and accordingly the status will be changed. Okay, so whenever you have to check the status of the flags, so you have to make it sure that you check it directly after the instruction. Okay, if you check it later on after some time, okay, you go on writing some instructions and you want to see what is the status of flag at after this instruction, but you check the status at this point. Okay, so this will not give you the status of the flags for this instruction. This will give the status of flags for this instruction, of course. Okay, because if you go from here to here, the status of flags has changed 3 times. In add C, the status may be different. In add B, since the data in the accumulator is not changed, you will get different status. Okay, in subtract D, again, it is arithmetic operation. The contents of A are modified according to the status will be different. Okay, so where you have to check the status, that you have to take care. Okay, after which instruction you want to check status, you have to check at that point only. You have not to check this states of the flags after so many instructions, and then you just say, okay, I'm going back, I'm going to see what is the status of the instruction which is was executed earlier. Oh no, it is not like that. Okay, this is what is the mistake generally we do when you check the status of the flags. So after every arithmetic operation, you have if you want to use the flags, you have to check the flag status immediately after that. Okay, so we will continue further. So I think this concept of these flags is clear to you. What are flags and how are the status is checked and what is basically the use of the flags. Okay.